Questions about congruences?
Professor, will you answer questions about the review also?
Yeah, of course. Anything.
Yeah, the last question of the review, can you go over that?
Okay, just 1 second.
I think it's question
Let me
15.
pull it up.
No problem.
Okay, so in the review, the last question, so this is review number 15. So Z mod MZ, this is the set of congruence classes modulo M. So, oops, excuse me 1 second, let me get rid of that. Sorry, so congruence classes mod M, and how many are there? The cardinality is exactly M, right? So this is the set, for example, of all the multiples of M, 1 plus MZ, 2 plus MZ, up to M minus 1 plus MZ, right? So this is the set of congruence classes mod M, and addition is defined as follows. If you have the congruence class MZ and the congruence A plus MZ and B plus MZ, and you add them, this is defined to be the congruence class of A plus B plus MZ. And we proved that addition of these congruence classes is well defined. I mean, what that means, for example, suppose you take M equal to 7, the congruence class 3 plus 7Z is the same as the congruence class of 24 plus 7Z, right? Because 3 is congruent to 24 mod 7. So we can add congruence classes, and under addition, Z mod MZ is a finite abelian group. But we also have multiplication. We define the multiplication of A plus MZ times B plus MZ to be the congruence class AB plus MZ. And this is also well defined. So for example, if you took 3 plus 7Z times 9 plus 7Z, what is that? That's 27 plus 7Z, which is the same as 6 plus 7Z. And if you take, for example, 24 plus 7Z plus times, I don't know, minus 2 times 2 plus 7Z, that should be the same thing, because 3 plus 7Z is the same congruence class as 24 plus 7Z. Right? We saw that here. And similarly, 2 plus 9 plus 7Z is the same as the congruence class 2 plus 7Z. And what is 24 times 2? It's 48. And what is 48 mod 7? 48 is congruent to 6 mod 7. So this is the same as 6 plus 7z. So this is just an example of the fact that multiplication of congruence classes is well defined. But and when you multiply congruence classes, the identity under multiplication is the congruence class 1 plus mz. Because if you take any congruence class, a plus mz, and multiply it by 1 plus mz, you get a times 1 plus mz, which is a plus mz, and in the opposite order as well. So this is the identity, but but under multiplication in general, z mod mz is not an abelian group under multiplication. For example, if you take 3 plus mz and you multiply it, let's say 6, take the congruence class of 3 mod 6 times any class a plus 6z. This is going to be 3a plus 6z, and that's not going to be equal to the identity 1 plus 6z, no matter what a you choose. So this congruence class does not have a multiplicative inverse, right? So if you look at all the congruence classes mod m, under multiplication, they do not form a group. But if we let z mod mz star, this means the set of all congruence classes a plus mz, where a and m are relatively prime, this is a group under multiplication. And we know that multiplication is associative. We have an identity. We know that multiplication is commutative. Must show that every congruence class a plus mz in this set of congruence classes that are relatively prime to the modulus m has an inverse. All right, so that means given a plus mz, must find a congruence class x plus mz such that a plus mz times x plus mz equals 1 plus mz. That's what it means to have a multiplicative inverse. This would be the inverse of a plus mz. This is the same as finding an x such that ax plus mz equals 1 plus mz, which is the same as being able to solve the congruence ax congruent to 1 mod m. But this always has a solution if the greatest common divisor of a and m is 1. That was our basic theorem about linear congruences. So we're choosing a congruence class relatively prime to m. That means a and m are relatively prime. So there does exist an integer such that ax is congruent to 1 mod m. And that means there's a congruence class x plus mz such that this times this is 1. And that means that when you check all the other conditions to be an abelian group, that the set of congruence classes relatively prime to m is a finite abelian group under multiplication. So that's actually a complete proof or a solution to the problem.
Professor.
Yeah.
So we don't have to include the fact that 1 is congruent to 0 mod 1. So that to just say that is good enough.
Sorry, the fact that 1 is congruent to what?
0 mod 1.
That's irrelevant.
Okay.
I mean, you don't need anything. We never look at congruence as mod 1. I mean, we can, but everything is congruent to everything else mod 1.
No, because I was saying, because I remember from when we did that you needed to find the lowest common, the greatest common divisor, and also check if B is congruent to 0 mod the GCD.
Right. Okay. So 1 is certainly congruent to 0 mod 1. That's true. But in fact, we proved that if A and M are relatively prime, the congruence AX congruent to B mod M always has a unique solution mod M. But you're right. This is, I'm using this fact without saying it, that to know that there's a solution. That's true.
Okay, I get it. Thank you, Professor.
Sure. Other problems or from lectures, from the textbook, from the homework?
Can we, Professor, can we do number 4 from the exam review?
Sure.
Thank you.
So problem 4 uses the Chinese remainder theorem. And Chinese remainder theorem says you can solve the congruence as X congruent to A mod M and X congruent to B mod N if and only if A is congruent to B modulo the greatest common divisor of M and N. So in this case, we have X congruent to 12 mod 25, X congruent to 22 mod 35. So with this notation, A is 12, M is 25, B is 22, N is 35. The greatest common divisor of M and N is the greatest common divisor of 25 and 35. That's 5. And A is congruent to B, that is 12 is congruent to 22 mod 5, because the difference is minus 10, and that's a multiple of 5. So we know there's a solution. And if there's a solution, if X is 12 mod 25, X has to be an integer of the form 12 plus 25y. And that integer, 12 plus 25y, has to be congruent to 22 mod 35. It says 25y has to be congruent to 10 mod 35. If we divide everything by 5, that's the same as saying 5y has to be congruent to 2 mod 7. Let's see, what's the solution of this congruence? Well, y congruent to 6 mod 7 is a solution, because 5 times 6 is 30, 30 minus 2 is 28, is divisible by 7. So y is a number of the form 6 plus, say, 7 times z. So the general solution will be x equal to 12 plus 25y. That's 12 plus 25, 6 plus 7z. 25 times 6 is 150. That's 162 plus 25 times 7, 175 z. So the complete solution, the general solution, is all x congruent to 162 mod 175. And of course, you note 175 is the least common multiple of 25 and 35. Let's just check. 162 minus 12 is 150. That's divisible by 25. 162 minus 22 is 140, and that's divisible by 35. So that is the solution. I mean, I might be going through this too quickly, so if you have any questions about anything I did, just ask me.
Professor, can you do 14?
Number
14.
14,
Yes.
okay. So number 14, we have integers a and m. M is positive, and a and m are relatively prime. So what is called the order of a modulo m is the smallest positive. You can't take 0 or negative numbers. The smallest positive integer, let's say k, such that a to the k is congruent to 1 mod m. And we know such a k exists because by Euler's theorem, a to the power phi of m is congruent to 1 mod m. And this is the Euler phi function. This is a positive integer. So there's some positive integer k with this property, and the smallest one is what is called the order. So that's the definition of the order. And why does the order of a divide phi of m? Well, suppose we divide phi of m by k. K is the order. It's the smallest integer with this property. So then phi of m is k times some quotient plus a remainder. And the remainder is always between 0 and k minus 1. So what does this say? We know that 1, this is Euler's theorem, 1 is congruent to a to the phi of m. This is just going to be all mod m. And phi of m is the same. Phi of m is k q plus r. And this is just a number to a power. So this is the same as a to the k times q times a to the r. Right? Any questions about this? This is, basically high school algebra, but at a little bit higher level. A to the kq, that's a to the k to the q. But k is the order of a to the k is 1. So this is just 1 to the q times a to the r, and 1 to any power is 1. So this says a to the r is congruent to 1 mod m. And again, r is the remainder, which is between 0 and k minus 1. But k is the order of a. K is the smallest positive integer with this property. And r is smaller than k, so it can't be positive. Therefore, r, it has to be 0. And if r is 0, phi of m is k times q. That is k, the order of a, divides phi of m. So that is arithmetic proof of this result. Okay. Any questions about that? Any question?
Yes, Professor, can you go over number 11, please?
Sure. So a complete system of residues or set of residues, same thing, system of residues modulo M is a set of M integers, one chosen from each congruence class modulo M. So for example, if you take M equal 8, you could just take the numbers 0, 1, 2, 3, 4, 5, 6, and 7. You have 8 numbers and one from each congruence class. What's another complete set of residues? Choose any number that's congruent to 0 mod 8. I don't know, 16. Choose any number congruent to 1 mod 8. I don't know, -7. Any number congruent to 2 mod 8. 42. Any number congruent to 3 mod 8. 83. Any number congruent to 4 mod 8. -4. Any number congruent to 5 mod 8. -11. Any number congruent to 6 mod 8. Well, 6, why not? Any number congruent to 7 mod 8. 807. So these 8 numbers, they're another complete system of residues mod 8. There's one from each congruence class. Right? That's all it is. For number 12, a reduced system of residues modulo M is a set of the order phi function, phi of M integers, one from each congruence class relatively prime to M. That is, each congruence class in Z mod MZ star. So for example, for M equal 8, Z mod 8Z star, the congruence classes relatively prime to 8 are 1 plus 8Z, 3 plus 8Z, 5 plus 8Z, and 7 plus 8Z. So what is a reduced system of residues modulo 8? You could take 1, 3, 5, and 8, 1, 3, 5, and 7. Or you could take, I mean, even from this reduced system, see here in this reduced system, 1, 3, 5, and 7, those are from the congruence classes relatively prime to 8. -7, 83, -11 at 807. Those are one each from the 4 congruence classes relatively prime to 8. -7, 83, -11, 807. These are both reduced systems of residues modulo 8.
Can you do question 7, please, Professor?
Yeah. So question 7, the Euler Fermat theorem states that if A and M are relatively prime, then A to the power phi of M is congruent to 1 mod M. Right? That's the are there from our theorem. And the proof, well, let's see. There are lots of ways to prove it. So let's just prove it using the proof that's in the text. Let's see. So the way I proved it in the book is the following. Suppose I let R, consisting of the numbers R1, R2, R3, up to R sub phi of M, be a reduced system of residues modulo M. So then Ri, each one of these, and M are relatively prime for all I from 1 up to M. So from each congruence class relatively prime to M, I choose one number. And then we use the following fact. If A is relatively prime to M and Ri is relatively prime to M, then ARI, when you multiply them, this number is also relatively prime to M. Because if this were greater than 1, there would be a prime number that divides M and ARI. But if a prime divides a product, it divides one of the factors. So it either divides A or it divides RI. But no prime divides M and A, and no prime divides M and RI. So M and ARI, these have to be relatively prime. Also, if I is different from J and ARI is congruent to ARJ mod M, this means that M divides the difference, ARI minus ARJ, which is A times RI minus RJ. So M divides this product, and Euler's lemma says that if M divides a product and it's relatively prime to one factor, then it has to divide the other factor. So by Euclid's lemma, M divides Ri minus Rj. So Ri is congruent to Rj mod M. So therefore, the set of numbers AR1, AR2, up to AR A times R sub phi of M, this is a set of phi of M integers, pairwise incongruent, that means no two of them are congruent, and relatively prime to M. So this is another reduced system of residues mod M. So there's a one-to-one correspondence between these numbers and these numbers, the numbers in the reduced residue system. So if I multiply all these together, AR1, AR2, up to AR sub M, this is congruent to the product of R1, R2, up to R sub M, mod M. But what do I have here? I have phi of it, this is phi of M. I have phi of M factors of A to the phi of M, R1, R2, up to R sub phi of M. congruent to R1, R2 up to R sub phi of M mod M. And I can cancel this. It's relatively prime to M. So A to the phi of M is congruent to 1 mod M. That's the proof of the Euler. That's a proof, the proof in the book and in my notes, in the talk, in the lectures. That's a proof of the Euler, of Euler's theorem.
Professor,
Yes,
you don't have to do the following question, but I have a concern about this question. This is question number 8. For K, can be K equal to 0? It
No.
said it's, no?
0 is not positive. It says smallest positive integer,
Okay,
Positive.
yeah,
greater than or
that
equal
was
to
my
1.
concern because, okay, great. Okay, thank you.
Sure.
Can you use the 13, Professor?
13? Yep.
Yes, about the fields.
So number 13, a field. Well, again, it depends. The definitions depend on what you know. So a field is a kind of a ring. So let's say a field is a set F with 2 operations, addition and multiplication, such that first F is an abelian group under addition. F star, which is F with 0 removed. So this is the non-zero elements, is an abelian group under multiplication. And addition and multiplication are linked by the distributive law. A times B plus C is AB plus AC for all A, B, and C in the set F. So that's what a field is. And if you take Z mod 4Z, which consists of the congruence classes 4Z, 1 plus 4Z, this is the same as 0 plus 4Z, this is all multiples of 4, 2 plus 4Z, and 3 plus 4Z. So Z mod 4Z star, if you take away 0, this is 0. This is 1 plus 4Z, 2 plus 4Z, and 3 plus 4Z. Let me write this as, well. This is Z mod 4Z with just the congruence class 4Z removed. Notice that, let me just call this something, I'll call this X. So 2 plus 4Z is in X, but 2 plus 4Z times 2 plus 4Z, 2 times 2 is 0 mod 4. This is 4Z, and that's not in X. So X is not closed under multiplication. So X is not a multiplicative group. Right? In a field, if you take away 0, everything that's left is a group under multiplication. That means it's closed under multiplication. And here, if I take away 0, I have these 3 congruence classes, but it's not closed under multiplication. So this doesn't form a group. So Z mod 4Z is not a field. Any questions about that? Okay, what about Z mod 5Z? So this is a field. What is Z mod 5Z star? This consists of the congruence classes 1 plus 5Z, 2 plus 5Z, 3 plus 5Z, 4 plus 5Z. What's the multiplication table? I'll just write 1, 2, 3, 4 to represent the congruence classes. Multiply them. You multiply them. 1 times everything is everything. 2 times 2 is 4. 2 times 3 is 6, which is 1 mod 5. 2 times 4 is 8, which is 3 mod 5. 3 times 2 is 6, which is 1 mod 5. 3 times 3 is 9, which is 4. 3 times 4 is 12, which is 2 mod 5. 4 times 2 is 8, which is 3. 4 times 3 is 12, which is 2. 4 times 4 is 16, which is 1. This is the multiplication table. So this is closed under multiplication. And every element has an inverse, like the inverse of 2 is 3. The inverse of 4 is 4. 4 times 4 is 1. So this is a field. I mean, we know it's a ring. We know that addition is an abelian group, multiplication. Well, here it is. All the properties of a field are satisfied. Okay. Any questions about why this is a field? We proved the properties of congruences, that addition and multiplication are associative. There's a distributive law. All those properties hold. The only thing you need to know to get to show that this is a field is that the non-zero congruence classes are closed under multiplication, and every element has an inverse. And from this table, you see the inverse of each element. The inverse of 1 is 1. The inverse of 2 is 3. The inverse of 3 is 2. The inverse of 4 is 1. Okay.
So
Any questions about that?
the addition table is not necessary, right?
Excuse me?
The table for addition is not necessary, right?
No, we know that Z mod MZ is always an additive abelian group for every M. It doesn't matter whether or not M is prime.
Okay, perfect.
Okay. But now, what about part D? So Z mod PZ star. So if A is prime to P, relatively, if A and P have no common divisor, if they're relatively prime, then there exists a B such that AB is congruent to 1 mod P. That's our basic theorem about linear congruences. So A plus PZ has an inverse, and the inverse is the congruence class B plus PZ. So every congruence class, every non-zero congruence class has an inverse. And of course, if A is prime to P and B is prime to P, then AB is prime to P, which means A plus PZ times B plus PZ, which is AB plus PZ. This is a congruence class relatively prime to P. This is in Z mod PZ star. So this is closed under multiplication, and every element has an inverse, and multiplication we know is associative, and we know there's a distributive law, and we know that multiplication and addition are both abelian operations. So we have a field.
Professor,
Yeah,
can you go over problem 6, part C?
the Chinese remainder theorem,
Problem 6,
problem 6.
yeah, part C.
So problem 6C. Prove M is prime if and only if phi of M is M minus 1. Let's see, so let's prove it in this direction. Suppose M equals P is prime. Then if you look at the numbers, 0, 1, 2, 3, up to P minus 1, the only number which has a factor in common with P is 0. The greatest common divisor of P and 0 is P. All of these numbers are relatively prime to P. A and P are relatively prime for all A from 1 up to P minus 1. So phi of M, or in this case, phi of P, phi of M, is M minus 1. So if M is prime, phi of M is M minus 1. So let's prove the opposite. I can either show that if phi of M is M minus 1, M is prime, or the contrapositive, I will show if M is composite, composite means not prime, then phi of M is less than M minus 1. And if M is composite, that means you can write M as A times B, where A and B are strictly between 1 and M. So if I look at the numbers 1, 2, 3, up to M minus 1 and 0, and A is in there somewhere, I cross out all the numbers which have a factor common with M that's bigger than 1. So of course 0 I cross out, but I can also cross out A, because A and M are not relatively prime. Right? Greatest common divisor of A and M is A, which is bigger than 1. So I've crossed out at least 2 numbers, so phi of M is at most M minus 2. It's not equal to M minus 1. And that's really all I need to say. No one asked me about number 8. It's nice to do some computational problems. You want to find the smallest k such that 2 to the k is congruent to 1 mod 17. So you could start taking all the powers of 2 until you get to 1. But of course, we know that k, we already proved this, k divides phi of 17, which is equal to 16. So k can only be a divisor of 16, 1, 2, 4, 8, or 16. So we just look at these powers. 2 to the first power is 2, which is not congruent to 1 mod 17. 2 squared is 4, which is not 1. 2 cubed is 8, which is not 1 mod 17. Sorry, I don't even need that. 2 to the fourth is 16, which is not 1 mod 17. 2 to the eighth is 256. 256 minus 1 is 255. If you divide that by 17, you get exactly 15. So 256, which is 2 to the eighth, is congruent to 1 mod 17. So the answer to problem 8 is 8. Oh, and problem 9, there's a typo. It says find the order of k modulo 7. It should say find the order of a modulo 7. That's the only, there's no k there in problem 9. Yep. Okay, any questions? Any more questions?
Yes, number 1.
Go ahead.
Can you do question number 10?
Well, yeah. The congruence class modulo M is the set of all integers congruent to A modulo M for some integer A. So take any integer. I mean, suppose M is 15 and A is 100,000. The set of all numbers congruent to 100,000 modulo 15 is a congruence class. And a commutative ring a ring R is a set with two operations, addition and multiplication, such that first, R is an additive abelian group. That means with respect to addition, R is an abelian group. Multiplication satisfies the following properties. ABC is A times BC for all A, B, and C in the ring in R. So it's associative. There's an identity, I'll call it 1 in R, such that A times 1 and 1 times A equals A for all A in the ring. We don't assume that elements have multiplicative inverses, and we have distributivity, the distribution law. A times B plus C is AB plus AC, and A plus B times C is AC plus BC for all A, B, and C in the ring. So this is what a ring is, and R is a commutative ring. If the multiplication is commutative, AB equals BA for all A and B in the ring. So that's the definition of a commutative ring. And all of the properties of congruences that we discussed, and I discussed today, in fact, every single one of them, shows that all of the properties of an abelian group under addition and multiplication satisfying these conditions and the distributive law, they all hold in Z mod MZ. So Z mod MZ is a commutative ring. Z mod MZ for all integers M. Positive. Is that it? Remember, I have office hours this afternoon and also on Tuesday. So there's time to log in before the exam, which is Wednesday, if you have any other questions.
Professor, can I just ask a
Can
quick
we
question?
ask-
Go ahead.
For two, are you going to have anything on the test for congruences with two variables, the X and the Y?
What do you mean?
So. So for, where are we here? 2, so section like 2, number 4, it's saying like 5x plus 7y is congruent to 3 mod 17. And then it lists another one, 2x plus 3y is congruent to -2 mod 17. So you have to find all solutions. So you're basically solving for x and y.
So I guess since I didn't put it on the review sheet, I will not have something like that on the exam.
Okay, thank you.
But let me solve one of those problems, just so you see how it's done, because it's exactly high school algebra, what you did without the congruences. So, because these are congruences to the same moduli. So this is section 2.2, number 4. So just the way in high school you would solve 5x plus 7y equals 3 and 2x plus 3y equals minus 2. 2 equations and 2 unknowns, right? This is a high school algebra problem. But this is not high school algebra, this is number theory. And these now are not equations, but they're congruences, but with respect to the same modulus. And how did you solve equations like this in high school? Well, one way was you added and subtracted multiples of one equation to another. But you can do the same with congruences. For example, I can take this first congruence and multiply it by 3. So if I multiply this by 3, I get, because you can multiply congruences, 5x plus 21y is congruent to 9 mod 17. And I can multiply the second congruence by 7. I would get 14x plus 21y is congruent to minus 14 mod 17. And you can add and subtract congruences. If I subtract, 15 minus 14 is 1. 21 minus 21 is 0. 9 minus minus 14 is 23 mod 7, mod 17, or the same thing, x is congruent to 6 mod 17. So for these two congruences, x has to be equal to congruent to 6. Plug in x equals 6, let's say, into this first congruence. You get 5 times 6 plus 7 times y is congruent to 3 mod 17. 30 plus 7y is congruent to 3 mod 17. Subtract 30, 7y is congruent to minus 27 mod 17. Minus 27 is congruent to plus 7 mod 17. So y is congruent to 1 mod 17. Let's just check by plugging into the second congruence. 2 times 6 plus 3 times 1 is 12, plus 3 is 15. 15 is congruent to minus 2 mod 17. So just by doing what you learned to do in high school, we could solve this pair of congruences because they're congruences to the same modulus. Okay. Nothing else?
Professor, number 1, can you go over, please,
Number 1, where?
from the review?
Well, that's exactly in the book. We define congruence, right? We know that A congruent to B mod M means M divides A minus B. And that's the definition. And if A is congruent to B mod M, that means A minus B is divisible by M is M times some number Q. And if B is congruent to C mod M, that means B minus C is some multiple of M, M times Q prime. If you add, the B's cancel, A minus C is M Q plus M Q prime, which is M times Q plus Q prime. So A is congruent to C mod M, right? And everything else is exactly the same. If A is congruent to B mod M and C is congruent to D mod M, this means A is B plus MQ. This means C is D plus MQ prime. So if you add, you get A plus C is B plus D plus M, Q plus Q prime. So A plus C is congruent to B plus D mod M. And if you multiply them, A times C, that's B plus MQ times D plus MQ. Multiply it out. You get BD plus MBQ plus M, this is a prime. You get BD plus M BQ prime plus MDQ plus M squared QQ prime. It's just multiplication. Factor an M out of this, and you get whatever you get. MQ, you get BQ prime plus DQ plus MQQ prime. So AC minus BAC is congruent to BD mod M, right? All right, that's all it is. Okay, any questions? Okay. All right, so again, there are office hours today and tomorrow, so there's plenty of time if you want to log on and ask me more questions. And our second exam is 9 o'clock on Wednesday morning.
Thank you, Professor.
Okay,
Thank you.
all right, bye all.
Bye-bye.